Statistics. Chapter 1. Statistics is the study of how we describe and make inferences from data. It's a branch of mathematics used to summarize, analyze, and interpret a group of numbers or observations. Two ways of evaluating information. Descriptive statistics, applying statistics to organize, summarize, and make sense of information, are typically presented graphically in tabular form or as summary statistic. Inferential statistics, applying statistics to interpret the meaning of information, to answer a question or make an actionable decision. Mark Twain, there are oral lies, damn lies, and statistics. Data are measurements of observations that are typically numeric. A datum is a single measurement or observation, usually referred to as a score or raw score. Remember, ISSR variable is measured property of each of the unit of analysis, age, GDP, household income, etc. Descriptive statistics, typically used to quantify the behavior researchers measure. Instead of listing each individual score or increase on an exam, we could summarize all scores by stating the average, mean, middle, median, or most common, mode, score among all individuals, which can be more meaningful. Inferential statistics is a conclusion research reached on the basis of evidence and reasoning. Allow researchers to infer or generalize observations made with samples to the larger population from which they were selected. Inferential statistics are used to help the researcher infer how well statistics in a sample reflect parameters in a population. Population parameter, a characteristic usually numeric that describes a population. Sample statistic, a characteristic usually numeric that describes a sample. The characteristics of the interest are typically descriptive analysis. Research methods and statistics. Science, the study of phenomena. Research method, or scientific method, a set of systematic techniques used to acquire, modify, and integrate knowledge concerning observable and measurable phenomena. Scales of measurement. Scales of measurements are rules for how the properties of numbers can change with different uses. Imply the extent to which a number is informative depends on how it was used or measured. Scales of measurement are characterized by three properties. Order, does a large number indicate a great value? Difference, does subtracting two numbers represent some meaningful? And ratio, does individual or talking the ratio of two numbers represent a meaningful value? So nominal does not have an order, no difference, and no ratio. Ordinal does have an order. Interval has an order and differences, and ratio has ratio, orders, and differences. S.S. Stevens, Harvard psychologist who coined the terms nominal, ordinal, interval, and ratio, nominal scales, measurements in which a number is assigned to represent something or someone, are often data that have been collected. Group classifications, no meaningful ranking possible, numerical coding. A person's sex, race, nationality. Coding. Words with numeric values is useful when entering names of groups for a research study into statistical programs as SPSS, because it can be easier to enter and analyze data. Ordinal scales. Measurements that convey order or rank alone. Finishing order in a competition, educational level, or rankings. Interval scales, measurements that have no true zero and are distributed in equal units. True zero when the value of zero truly indicates nothing on a scale of measurement. So it's rating scale, temperature, Celsius, etc. And ratio scale, measurement that have a true zero and are distributed in equal units are the most informative scales of measurement. Length, height, weight, and time. We always first need to know the level of measurement in order to know which statistical techniques we may use for a given variable. Nominal, ordinal, qualitative variables, interval ratio, quantitative variables. Types of variables for which data are measured. Continuous variable, measured along a continuum at any place beyond the decimal point, can be measured in fractional units. Discrete variable, measured in whole units or categories that are not distributed along a continuum. Quantitative variable varies by amount, and qualitative variable varies by class. So discrete variable measured in whole units or categories that are not distributed along a continuum, and continuous variable can be measured in fractional units. Measures of central tendency. Statistically, measures of locating a single score that is most representative or descriptive of all scores in a distribution are values at or near the center of a distribution. Although we lose some meaning anytime we reduce a set of data to a single score, statistical measures of central tendency ensure that the single score meaningfully represents a set of data. Population size n, sample size small n. Mean, arithmetic mean or average, balance point in a distribution, works for interval and ratio level of measurement. Its value shifts in a direction that balances a set of scores. In the sum of E, a set of scores x divided by the total numbers of scores summed in either a sample n or population n. The mean can be misleading when a data set has an outlier because the meaning will shift towards the value of that outlier. Outliers in data set influence the value of a mean but not the median. Changing an existing score will change the mean. If you increase the value of an existing score, the mean will increase. If you decrease the value, the mean will decrease. Adding a new score or removing an existing score will change the mean unless that value equals the mean. Adding, subtracting, multiplying, or dividing each score in a distribution by a constant will cause the mean to change by that constant. Summing differences of scores from the mean equals 0. When the mean is subtracted from each score, then summed, the solution is always 0. The sum of the squares' difference of scores from their mean is minimal. The smallest possible positive number greater than 0, so SS. Weighted mean. The combined mean of two or more groups of scores in which the number of scores in each group is disproportionate or unequal. Can be used to compute the mean for multiple groups or scores when size of each group unequal. Some samples have more scores than others. The weighted mean is larger than the arithmetic mean when the larger sample scored higher. Median, the middle value in a distribution of data listed in numeric order, works for ordinal, interval, and ratio levels of measurement. The median position is not as sensitive to outliers as mean. The 50th percentile of a cumulative percent distribution can be used to estimate the value of median. Mode, value in a data set that occurs most often or most frequent, is often reported in research journals with a mean or median, works for nominal, ordinal, interval, and ratio levels of measurement. Choosing an appropriate measure of central tendency. The choice of which measure to select depends largely on the type of distribution and the scale of measurement of the data. Normal distribution, symmetrical, Gaussian, or bell-shaped distribution, is a theoretical distribution in which scores are symmetrically distributed above and below the mean. The median and the mode are at the center of the distribution. The mean is most useful for describing normally distributed variables and measures of an interval or ratio scale, because all scores are included in its calculation. Describing normal distributions, when your data is continuous, the mean, median, and more are the same values located in the center of the distribution. Describing interval and ratio scale data, data that can be described in terms of distance that scores derivate from the mean. Differences between two scores are meaningfully conveyed for data on an interval or ratio scale only. The median is often used for interval ratio that have skewed distributions and measures on an original scale. Skewed distribution. Distribution of sources that include outliers or scores that fall substantially above or below most other scores in a dataset. Positively skewed distribution. Distribution of scores in which outliers are substantially larger than most others. Negatively skewed distribution. Distribution of scores in which outliers are substantially smaller towards the left of the tail graph than most others. So positively towards the right, negatively towards the left. Describing skewed distribution. The value of the mean is pulled towards the skewed data point in a positively skewed distribution. The mean is greater than the mode. In a negatively skewed distribution, the mean is less than the mode. The location of the median is unpredictable and can fall on any side of the mode, depending on how the scores are distributed. Outliers distort the value of the mean, making it a less meaningful measure for describing all data in a distribution. The median is not influenced by the value of the outliers and therefore is more representative of all data in skewed distribution, being the most appropriate measure of central tendency. To describe these types of distribution, describing ordinal scale data, the median is used to describe ranked or ordinal data that convey direction only. The fifth person to finish a task took longer than the first person to finish a task, because the distance, deviation, or ordinal scale scores from their mean is not meaningful. The mode can be used for nominal, ordinal, and interval ratio variables, describing model distributions. Model distributions, distribution of scores in which one or more scores occur most often or most frequently. Unimodal distribution, distribution of scores in which one score occurs most often or most frequently, has one mode. Bimodal distribution, distribution of scores in which two scores occur more often or most frequently, has two modes. The mean and the median are typically located between the two modes. Multimodal distribution is a distribution of scores where more than two scores occur most often and frequently, has more than two modes. Non-modal distribution, rectangular distribution, distribution of scores where all scores occur at the same frequency, has no mode. The mean or median can be used to describe data. Describing nominal scale data. The mode is used to describe nominal data that identifies something or someone. Because a nominal scale value is not quantity, it does not make sense to use the mean or median to describe this data. Anytime you see phrases such as most often, typical, or common, the mode is being used to describe these data. Measure of central tendency, mean, median, mode, shape of distribution, normal, skewed, modal, measurement scale, interval ratio, ordinal, and nominal. Chapter 4. Variability. Measuring variability. Variability measure of the dispersion or spread of scores in a distribution and range from 0 to infinity. Determine how dispersed scores are in set of data. Measures of variability. Range, ordinal, interval ratio, distance between highest and lowest score. Range, largest value minus smallest value. Always reported together with maximum and minimum scores. Sensitive to outliers. Interquartile range. IQR, ordinal, or interval, or ratio, based on quartiles that split our data into 4 equal groups or cases. Interquartile range, upper quartile, 75th percentile, lower quartile, 25th percentile. Little influence of outliers because IQR excludes the top and bottom 25% of scores in a distribution. The median for all data, median quartile. Variance is a measure of variability for the average squared distance that scores deviate from their mean. Based on the sum of squares, the squared differences from the mean. Is a preferred measure of variability because all scores are included in its computation. Variance can be computed for data in populations and samples. For the calculation of a variance, it matters whenever we have sample data or population data, typically same data. The definitional formula for variance. The SS produce the smallest possible value for deviation of scores, form their mean, difference from 0, minimizes error. The SS is computed in the same way for sample variance and population variance. If a population has a variance of x, on average, any sample select from a population should also have a variance of x. If not, the sample variance is biased. Why are the two different variance formula for sample data and population data? We often use the sample variance as an estimator for the population variance. When we calculate sample variances, we therefore define divide by n minus 1 to arrive at the unbiased estimator of the population variance. This is particularly relevant in small sample. How can we interpret the value of a variance? We don't, but everything is meaningful in comparison. When comparing variances across groups, we can make comparative statements about more or less dispersion around the mean. For the purpose of interpretation, we calculate another measure of variability. The computational formula for variance, the raw scores method for variance. Squaring decimals often requires rounding, and the mean is often a decimal, resulting in rounding errors. Computational formula for variance is an alternative to solve this problem. Fractals, the measures that divide a set of data into two or more equal parts. Fractals include the media, quartiles, deciles, and percentiles, which split data into 2 parts, 4, 10, and 100 parts respectively. Deviation, the difference of each score from its mean. The sum of the deviation of scores from their mean is 0. Biased estimator, any sample statistics such as sample variance when we divide SS by n, obtained from a randomly selected sample that does not equal the value of its respective population parameter. Unbiased estimator, any sample statistics such as the sample variance when we divide SS by n minus 1, obtained from a randomly selected sample that equals the value of its representative population parameter. Degrees of freedom for sample variance. The number of scores in a sample that are free to vary when the sample mean is known. All scores except one are free to vary in a sample. The standard deviation. The root mean square deviation is a measure of variability for the average distance that scores deviate from their mean. It's calculated by taking the square root of the variance. Interval ratio is the square root of a variance, an appropriate measure of a sample distance to the mean. Standard deviation is SD. There's formula for sample and population. For normally distributed variables, we can use the SD to make statements about this distribution. Empirical rule. At least 68% of all scores lie within 1 SD of the mean. At least 95% of all scores lie within the 2 standard deviations of the mean. At least 99.7% scores of all scores lie within 3 standard deviations of the mean. The standard deviation is always positive. The standard deviation is used to describe quantitative data. The standard deviation is most informative when reported with a mean. The value of the standard deviation is affected by the value of each score in a distribution. Adding or subtracting the same constant to each score will not change the distance that score deviate from a mean. Hence, the standard deviation remains unchanged. Multiplying or dividing each score using the same constant will cause the standard deviation to change by the constant. Chapter 6. Probability. The normal distribution in behavioral science. The behavioral data that researchers measure often tend to approximate a normal distribution, in which scores are symmetrically distributed above and below the mean, the median, and the more at the center of the distribution. Characteristics of a normal distribution is mathematically defined. Rarely do behavioral data fall exactly within the limits of a mathematical formula. When we say that data are normally distributed, we mean that the data approximate a normal distribution. The normal distribution is so exact that it is impractical to think that behavior can fit exactly within the limits defined by the formula. It's theoretical. Data can be normally distributed in theory, approximation. The mean and the median and mode are located at the 50th percentile. Half of the data fall above the mean, one median and the mode, and half fall below. The normal distribution is symmetrical. The distribution of data above and below the mean are the same. The mean can equal any value. The standard deviation can equal any positive value greater than 0. The total area under the curve of an normal distribution is equal to 1. Proportions of area under a normal curve are used to determine the probabilities for normally distributed data. The tails of a normal distribution are asymptotic. The tails of a normal distribution never touch the x-axis, so it's possible to observe outliers in a dataset that is normally distributed. The standard normal distribution is this distribution, a normal distribution with a mean equal to 0 and a a standard normal deviation equal 1. The standard normal distribution is distributed in z-score units along the axis. So standard normal distribution, z-score, used to determine the probabilities of a certain outcome in relation to all other outcomes. To estimate probabilities under the normal curve, we determine the probability of a certain outcome in relation to all other outcomes. Z-score, a value of the x-axis of a standard normal distribution. The numerical value of a z-score specifies the distance of the number of standard deviation that a value is above or below the mean. Standard normal transformation, the z-transformation, a formula used to convert any normal distribution with any mean and any variance to a standard normal distribution with a mean equal to 0 and a standard deviation equal to 1. To locate where a score is in any normal distribution would be in the standard normal distribution, the mean is in any normal distribution corresponds to a z-score equals 0. Z is x minus mu делить на O for a population of scores, or Z равно x минус m большая делить на standard deviation for a sample of scores. И Z это у нас standard normal distribution. The unit normal table, a brief introduction. The unit normal table, z-table, type of probability distribution table displaying a list of z-scores and the corresponding probabilities or proportions of area associated with each z-score listed. Column A lists the positive z-scores for the negative z-scores below the mean. The normal distribution is symmetrical. Scores are listed from z0 at the mean to z4 above the mean. Column B lists the area between a z-score and the mean. The first value of the area listed in column B is 0.000, which is the area between the mean, z0, and the mean. As the z-score moves away from the mean, the proportion of area between the score and the mean increases closer to 0.5, or the total area above the mean column. Column C lists the area from a z-score toward the tail. The first values is 0.5, which is the total area above the mean. As a score increases and therefore moves closer to the tail, the area between the score and the tail decreases closest to 0. То есть представляем bell curve, и это A, B, C часть. Locating proportions. We can use the unit normal table to locate the proportion, and therefore the probability, of a score in a normal distribution. Transform a raw score x into a z-score. Locate the corresponding proportions for the z-score in the unit normal table. Locating proportions above the mean. To locate the proportion, look in column A in the unit normal table for the z-score equal to the one measured in step 1. The proportions toward the tail is listed in column C. Locating proportions below the mean. To locate the proportion, look in column A in the unit normal table for a z-score equal to the one measured but positive. A proportion given for a positive z-score will be the same for a corresponding negative z-score. The proportion of a z-score towards the lower tail is listed in column C. Locating proportions between two values, the proportion between the mean and z-score of 1 is the same as that for minus 1. The total proportion between the value below the mean and the value above the mean is the sum of the proportion for each score. Locating scores. Finding scores in a given percentile can be useful in certain situations. Selecting samples from populations. Inferential statistics and sampling distributions. Sampling distribution, a distribution of a sample means or sample variances that could be obtained in sample of a given size from the same population. Researchers use the sample statistics they measure in a sample to make inferences about the characteristics or population parameters in a population of interest. Sampling and conditional probabilities, random procedure to select a sample to avoid bias. Sampling without replacement, most common sampling method in behavioral research. Each participant or item selected is not replaced before the next selection. The probability of each selection are not the same and are conditional. First draw P equals square market A делить на total number of squares. Sampling with replacement. Each participant or item selected is replaced before the next selection. To ensure that each individual or item has the same probability of being selected, this method is used to develop of a statistic theory. It is typically not necessary to use this method in behavioral research because the population of interests are large. Sample design. Specific plan or protocol for how individuals will be selected or sampled from a population of interest. Does the order of participants matter? Determines how often people in population can be selected. Do we replace each selection before the next draw? Sampling strategy, the basis of statistical theory. Theoretical sampling is used in development of the theories that have led to statistics as a branch of mathematics. In theoretical sampling, the order of selected individuals matter, and each individual selected and replaced before sampling again with replacement. Total numbers of samples possible, NN. Sampling strategy most used in behavioral researches. For most studies in behavioral science, order does not matter because we do not care about the order in which participants are selected. In experimental sampling, the area of selecting individuals does not matter, and each individual selected is not replaced before selecting again. Total number of samples. Sampling distribution. The mean. The population mean, mu, is computed by summing all scores in the population and dividing by the population size. The average sample mean is computed by dividing the sum of the sample means by the total number of samples summed. The sample mean is an unbiased estimator of a value of a population mean, follows the central limit theorem, and has a minimum variance. Central limit theorem explains that regardless of the distribution of scores in a population, the sampling distribution of a sample mean selected at random from the population will approach the shape of a normal distribution. As the number of samples in the sampling distributions increases, hypothetical distribution. Central limit theorem explains that regardless of the distribution of scores in a population, the sampling distribution of sample means selected at random from the population will approach the shape of a normal distribution. At least 95% of all possible sample means we could select from a population are within 2 standard deviations of the population mean. A distribution of a sample mean has a minimum variance, has a different standard deviation than the population distribution. Variance of a sample distribution of the sample means. Big M sample mean in each possible sample, mu M is the mean of the sampling distribution, and n the total number of possible samples that can be selected. The standard error of a mean. The standard deviation of a sampling distribution of means, it is the standard error of distance that sample mean values deviate from the value of a population mean. Tells us how far possible sample means deviate from the value of a population mean. Will be Skinner that the normal distribution of variance is the population. Take the square root of a variance. OM equals O, delete na корень is n. Sampling distribution, the variance. Sampling distribution of a variance to determine how the sample variances we could select from the population compared to the value of a population variance calculated. Unbiased estimator. A sample variance is an unbiased estimator when the sample variance we obtain is a randomly selected sample equals that the value of the population variance on average. The mean of the sampling distribution of the sample variance is the sum of the sample variance we could select divided by the total number of samples summed. On average, the sample variance is equal to the population variance when we divide SS by degree of freedom. This makes the sample variance an unbiased estimator of the population variance. If we divided SS by n, the result would be that we underestimate the population variance on average, which would make the sample variance a biased estimator on the population variance. Skewed distribution rule. Regardless of the distribution of a score in a population, the sampling distribution of a sample variance select at random from that population will approach the shape of a positively skewed distribution. As the number of samples is the sampling distribution increases. No minimum variance. Although the sample variance equals the population variance on average, the distribution of all other sample variances can vary far from the population variance when we divide SS by DF. The distribution of a sample variance is minimal only when we divide SS by n, but it's better for the sample variance to be unbiased because the primary use of a sample statistic is to estimate the value of population parameters, and this estimate must be unbiased. Then for a distribution of a sample variance is to vary minimally from the population variance. For this reason, the sample variance is calculated by dividing SS by df. The standard error of a mean. Variance of a sampling distribution of sample mean. The standard error of a mean, a numeric measure of sampling error within larger values indicating greater sampling error or greater differences that can exist from one sample to the other. Sampling error. The extent to which sample means select from the same population differ from one another. This difference, which occurs by chance, is measured by the standard error of a mean. Factors that decrease standard error. The larger the standard deviation is the population, the larger the standard error, bigger deviation. The standard deviation is low, it means that the sample is more stable. The law of large numbers explains that the larger the size sample, the smaller the standard error. Standard normal transformation with sampling distributions. Z transformation for sampling distributions use a formula when the exercise talks about sample means. The Z transformation is used to determine the likelihood of measuring a particular sample mean from a population with a given mean and variance to locate the proportion and the probability of selecting sample mean. In any sampling distribution, we 1. Transform a sample mean into a z-score and then locate corresponding proportions of the z-score in the unit normal table. To locate the proportion and the probability of selecting a sample mean in any sampling distribution, we transform a sample mean into a z-score and then locate the corresponding proportion for the z-score. Inferential statistics and hypothesis testing. Inferential statistics allows us to observe samples to learn more about the behavior in a population that are often too large or inaccessible to observe. We use samples because we know how they are related to populations. The sample mean is an unbiased estimator on the population mean. On the basis of the central limit theorem, we know that the probability of selecting any sample means value from the same population in normal distribution. We expect the sample mean to be equal to the population mean. Principle of hypothesis testing. Significance testing. We test a hypothesis about a parameter of a population mean using sample data measured in a sample. Hypotheses are therefore always about populations, never about samples. Tests of significance are used to determine the likelihood that a hypothesis about a population parameter is true. The null hypothesis of equality, is a statement about a population parameter such as the population mean that is assumed to be true. We always start by formulating a null hypothesis about a population parameter. Very often the H0 is not what the researchers expect. The only reason we're testing the H0 is because we think it is wrong. Typically, we therefore try to reject the H0. The opposing hypothesis is the H0 is called the alternative hypothesis. H1, always called the research hypothesis, is a statement that directly contradicts a null hypothesis by stating that the actual value of a population parameter is less than, greater than, or not equal to the value stated in the null hypothesis. We can never prove our alternative research hypothesis H1 about the population directly. We can only show that the H0 is unlikely to be true. In significance tests, we first assume H0 to be true and then see how unlikely it is given the sample data that we just obtained. If H0 turns out to be very unlikely, we reject it and therefore accept H1. How unlikely is unlikely enough to reject H0? What threshold to use? We call this threshold the level of significance, or alpha, based on the probability of obtaining a statistic measure in a sample if the value stated on the H0 were true. In social sciences, we typically use a 0.05 level of significance, alpha 5%, because regardless of the distribution in a given population, the sampling distribution of a sample mean is approximately normal. Hence, the probability of all other possible sample means we could select are normally distributed. Meaning, we make sure that the probability of falsely rejecting a true null hypothesis is not greater than 5%, or the chance of the null hypothesis being true despite the data we have is not greater than 5%. Level of significance. Type 1 error. Probability that you are going to make a mistake and accept H1 when you should have accepted H0. Type 2 error is the probability of retaining a null hypothesis that is actually false. Type 3 error, when we fail to reject H0 because we placed the rejection region in the wrong tail. Power in the hypothesis testing. The probability of rejecting a false null hypothesis. Specifically, it is the probability that a randomly selected sample will show the null hypothesis as false when the null hypothesis is indeed false. 4 steps in significance testing. Stage H0 and H1. Set the level of significance to be 5%. Compute the test statistics. One independent sample z-test is z obtained, m minus mu, delete na o, delete na korень is n. On independent sample t-test, everything is same but alpha hat. Make a decision to reject accept 0-1 decision about H1. H0. Compare the calculated test statistic obtained value with a critical value found in a table. Critical value, the cutoff value that defines the boundaries beyond which less than 5% of a sample mean can be obtained if the null hypothesis is true. Sample means obtained beyond a critical value will result in a decision to reject the null hypothesis. Obtain the value of a test statistic. When obtained value is more than critical value, we reject H0. Rejection region. Region beyond the critical value in a hypothesis testing, where value of a test statistic is in the rejection region, we decide to reject the null hypothesis. Otherwise, we retain the H0. So again, compare the calculated test statistic, obtained value with a critical value, and if obtained value is bigger than critical value, we reject H0. Idea behind the one independent sample z-test. We use z-test when the standard deviation is known. Independent, the sampling data, each case is independent of the other. No direct effect between data, no causality between one person to the other. Non-directional, two regions, 2.5% level of significance each. If the z-value is higher, it is more difficult to reject H0. We retain H0. Chapter 9. T-test. One independent sample t-test. 3 assumptions for a one sample t-test. Normality, data is the population being sampled are normally distributed in larger samples. SE is smaller and this assumption becomes less critical as a result. Random sampling, independence. The outcome does not influence another. Using random sampling usually satisfies the assumption. So one independent sample t-test, normality, random sampling, and independence. We use t-test when the standard deviation is unknown. As the estimate of a sigma, we use the sample SD. Estimated standard error. Estimate of standard error of a sampling distribution of a sample mean selected from a population with an unknown variance. It is an estimate of the SE or SD that sample mean deviate from a value of a population mean stated in the null hypothesis. Know the degrees of freedom for the sample t-test, Tf equals n minus 1. As sample size increases, Df also increases. If obtained value is bigger than critical value, we reject H0. The larger the sample size, the more closely a t-distribution estimates a normal distribution. There is a greater probability of obtaining sample means that are further from the value stated in H0 in small samples. As sample size increases, obtaining sample means that are further from the value stated in the null hypothesis becomes less likely. The result is that critical values got smaller and sample size increase. T-test in SPSS. The output will not tell us directly whenever or not to reject H0. SPSS calculate a p-value, the probability of obtaining a difference between the sample mean and the population value we tested it against, at least as large as the one that was obtained under the assumption that H0 is true. P-value is the probability of falsely rejecting H0, type 1 error. If p-value is equal or bigger than alpha, we retain H0. If p-value is smaller than alpha, we reject H0 and retain H1. When p is low, H has to go. SPSS always assumes a non-direction, H1, and thus gives us the p-value for an assumed two-tailed rejection region. If our H1 is direction, we divide the p-value by 2 before comparing it to our alpha. The p-value, sig, is the region past the t obtained into the tail. As the t gets larger, the region gets smaller, and so p-value becomes smaller. The same t-value obtained for a two-tailed H1 or more likely to reject the H0 under a directional H1, assuming M is the correct direction. When P is low, H has to go. Two independent sample t-test. Independent samples are the selection of participants such as the different participants are observed one time in each sample of group. Two independent sample t-test is a statistical procedure used to compare the mean difference between two independent groups. This test is specifically used to test hypotheses concerning the difference between two population means, where the variance is one or both population is unknown. In terms of a null hypothesis, we state the mean difference that we expect in the population and compare it to the differences we observe between the two sample mean in our sample. For assumptions, normality. Data is the population being sampled are normally distributed in larger samples. Random sampling. Independence. One outcome does not influence another using random sampling. Equal variances. The variance in each population are equal to each other. This assumption is usually satisfied when the larger sample variance is not greater than 2. So for two independent sample t-test, normality, random sampling, independence, and equal variance. Estimated standard error for the differences. Estimate of a SD of a sampling distribution of the mean differences between two sample means. It is an estimate of the SE or SD, and the mean differences can be expected to deviate from the mean differences stated in the null hypothesis. The higher the SE, the more likely is to retain H0 because more difficult it is to generalize it. That's all we need to know. We don't need to know formulas below for now. Pooled sample variance. The mean samples variance of two samples when the sample size is unequal. The variance in each group of a sample is weighted by its respective degrees of freedom. The larger n is, the better the estimate of sample variance will be. When we have equal sample sizes, we do not have to weight each sample variance by its respective df. This statistic for a two-independent sample t-test. The Levene's test for equality of variances. The math behind the independent sample t-test is different depending on if we can assume the sigma of the two groups to be equal. In order to make this decision, we first need to Levene's test for equality. Levene's test is concerned with a dispersion variance of population, no directionality in H1. For the Levene's test, SPSS calculates a p-value, the chance of falsely rejecting the H0 of that test. The two population variances are equal. If p-value is bigger or equals alpha, we retain H0. If p-value is smaller than alpha, 0.05, we reject H0 and retain H1. Once we know whenever or not to assume equal variances in the population, we can look at the p-value of the actual test and reject or access its H0. The Levene's test is not final test, but leads you to your final conclusions. If you don't reject H0, it means equal variance is assumed first row when turned to p-value of a t-test in the equal variances assumed row and compare it to the alpha. Chapter 11. Point estimation and interval estimation. Estimation, statistical procedure in which a sample statistic is used to estimate the value of an unknown population parameter. We use estimation to measure the mean or mean differences in a sample. But instead of making a decision regarding a null hypothesis, we estimate the limit within which the population mean or mean differences is likely to be contained. Two types of estimation are point estimation and interval estimation. Point estimation is the use of sample statistics, sample mean, to estimate the value of a population parameter. Sample parameter. Population is an unbiased estimator. The sample mean will equal to the population mean on average. We have no way of knowing for sure whenever a sample mean equals the population mean. Interval estimation is a statistical procedure in which a sample of data is used to find the interval of a range of possible values within which an unknown population parameter is likely to be contained. Confidence interval is the interval of range of possible values within which an unknown population parameter is likely to be contained. Sample means always are some known in distance away from the population mean, which means that sample mean does not accurately reflect the population mean. So based in the sample mean, we want to estimate in what general area the population mean is likely to be. Final statement will look something like this. We can conclude with 95% confidence that the population mean for our studying for ISL lies between 1706 and 22. Level of confidence. The probability or likelihood that an interval estimate will contain an unknown population parameter. Population mean. Confidence limits boundaries. Upper and lower boundaries of a confidence interval give within a specified level of confidence. 53%, 3% believe in ghosts. If we add or subtract 3% from each point estimate, we find that we can be confident that, on average, 50 to 56 of Americans believe in ghosts. If we want to be 95 confident, we use the critical values of z for the 0.05 level, two-tailed 2.5% on both sides, thus looking for 0.025. So 95 is 0.05, 90 is 0.10, 99 is 0.01. What is estimating? The population mean, the population point estimate. The population mean, the sample mean is used to estimate the population mean, very precise. The interval estimate, the population mean, a range of values is used within which the population mean is likely to be contained, and less precise. The process of estimation. To find the interval estimate, we compute the estimated SD and then we add and subtract the values of the point estimate. Using the empirical rule, we know that at least 68% of all possible sample means fall within the first SE of the mean. If we add and subtract one SE from a sample mean, we find that the true population mean is between 3.5 and 4.5 at a 68% level of confidence. This is the level of confidence because at least 68% of all possible sample means are contained within this range or interval. How to estimate a population mean using points estimate and interval estimate. Compute the sample mean and SE. Choose the level of confidence and find the critical values at that level of confidence. Compute the estimation formula to find the confidence limits. Population mean equals point estimate plus minus interval estimate. Estimation for one sample z-test. When we know the population variance, we can compute the one sample z-test. An alternative approach is to use estimation to estimate the value of a population mean. We use the estimation formula for one sample z-test to identify the confidence limits within which the true population mean is likely to be contained. The estimation formula, when SD is known with m plus minus z, typically we don't know that SD is the population and have to use the critical values of t and use sigma hat, estimation of standard deviation population, instead of sigma. The estimation formula with standard deviation is known as m plus minus t. If we need to be more confident about our statements, find appropriate t-value for the level of confidence. T-value tend to be bigger. Increasing k, a shift analyzing variance. The level of factor, k, the number of groups or different ways in which an independent quasi-independent variable is observed. A one-way between subject ANOVA, an introduction to analysis of variance, is a statistical procedure used to test hypotheses for one factor with two or more levels. Concerning the variance among groups means that test is used when different participants are observed to each level of factor, and the variance in any population is unknown. If the mean in each group significantly vary, the larger the differences are between group means, the larger the variance of group means will be. A between-subject design is a research design in which we select independent samples, meaning that different participants are observed at each level of a factor. With a f-test, we investigate to what extent the categories of an independent ordinal nominal variable help us to explain the variation of a dependent-independent ratio variable. The dependent variable is an interval ratio variable, ANOVA for interval or ratio. ANOVA is a statistical procedure used to test hypotheses for one or more factors concerning the variance among two or more groups means. Where the variance is one or more population is unknown, is an extension of the independent sample t-test, and it can be used for comparing more than two groups. The f-test is the main test of significance of the ANOVA, and used when comparing two or more groups. The H0 for the f-test states that in the population all group means are equal. In the population that means of happiness are equal across all the groups. The H1 states that in the population at least one group mean differs from the other. The H1 is always non-directional. H1, there are differences across groups on mu. Once we have rejected H0, we need a post hoc test that tells us which groups differ significantly from the rest. Two ways to select independent samples. Select a sample from two or more populations used for a quasi-experimental research method, which is a research design that does not have a comparison group or includes a factor that pre-exists cannot be manipulated. Select one sample from population and randomly assign participants in the sample to two or more groups. Used for experimental research method, which is research design that includes randomization, manipulation, and control. The only way to achieve an experiment using the between-subject design is randomly assign participants. For ANOVA, n number of participants per group, and number of total participants in study. Sources of variation and the test statistics. Between groups variation. The variation attributes to mean differences between groups. A source of variation. Any variation that can be measured in a study in the one way between subjects ANOVA. There are two sources of variation. Variation attributed to difference between group means and variation attributed error. Within groups, variation, the variation attributed to mean differences within each group. The source of variation cannot be attributed to or caused by having different groups, and therefore called error variation. A net distribution, a positively skewed distribution derived from sampling distribution of F ratios. In analysis of variance, we distinguish between three different types of variances. Total variance, how much all x vary around the grand mean. Variances between groups, MS, how much the group mean vary around the grand mean, and variance with groups, how much all the x vary around their respective group means. As the value of the test statistic increases, the likelihood of rejecting H0 increases. Larger value indicate less probable H0s, and also p-value decreases. The value of f is defined as f, important for theory questions. The value of f gets larger, making it easier to reject H0. In situations where either or both group means differ more, the groups are more homogeneous. The f gets larger when the groups are more homogeneous and group means differ more. Degrees of freedom. The critical value for an ANOVA is the cutoff value for the rejection region. Two sources of variation for the one way between subjects ANOVA, two degrees of freedom. The degrees of freedom between groups are the degrees of freedom associated with the variance of a group means in the numerator of the test statistics. They're equal to the number of groups. The degrees of freedom error, degrees of freedom within groups, are degrees of freedom associated with the error variance in the denominator. They're equal to the total number, sample size, n minus the number of groups. The one way between subjects ANOVA. We compute this test when we compare two or more group means in which different participants are observed in each group. Post hoc. Once we reject the H0 of the F test, we need to conduct a post hoc test to determine which means differ significantly from each other. Schaeffer's test is similar to two-sample t-test. It runs through all possible pairs of group means and examines their means differences. For each pair of group means, the H0 of the Schaeffer's test state that their population mean are equal. For each pair of groups, the post hoc test tells us the sample mean differences, first group mean minus second group mean, whenever this differences is statistically significant at 0.05 level. Correlation. Correlation, a statistical procedure used to describe the strength and direction of the linear relationship between two factors. The statistics used to measure correlation coefficient, are describing a correlation. A correlation can be used to describe the pattern of a data point for the values of two factors, described by the direction and strength of the relationship between two factors. Correlation coefficient. Correlation, a statistical procedure used to describe the strength and direction of the linear relationship between two factors. Determine whenever the pattern observed in a sample is also present in the population from which the sample was selected. Scatter plot. Graphical display of discrete data points used to summarize the relationship between two variables. Pairs of values for x and y are called data points. In scatter plot, the independent variable x is always put in the horizontal axis. X is the independent variable. Each dot represents a case and its position reflects the case value for x and y. Provides an intuitive, straightforward way of examining the relationship between two interval ratio variables. We need a measure of association to express the strength and direction of a relationship in a single, easily interpretable number, the correlation coefficient Pearson's R. The direction of a correlation coefficient R is used to measure the strength and direction of a linear relationship or correlation between two factors. The value of error ranges from -1 to +1. Values closer to +1 indicate a strong correlation. The sign of correlation indicates the direction of the correlation. A positive correlation is a positive value of R that indicates that the values of two factors change in the same direction. As the values of one factor increase, the values of a second factor also increase. A negative correlation is a negative value of R that indicates that the value of the two factors change in different directions, meaning that the values of one factor increases, the value of second factor decreases. The strength of a correlation. The closer a correlation coefficient is to R is 0, the weaker the correlation and less likely the factors are related. The closer a correlation coefficient is to R ±1, the stronger the correlation, and the more likely that two factors are related. Regression line, the best fitting straight line to set off a data point. A best fitting line is the line that minimizes the distance of all data points that fall from it. Scores are more consistent and the closer they fall to a regression line. Pearson's correlation coefficient, used to determine the strength and direction of a relationship between two factors or an interval or ratio scale of measurement. Each score should be transformed into a z-score. Pearson's formula. First calculated standard deviation of x and y. Pearson's R, a measure of associations for interval ratio variables. Covariance, the extent to which the values of two factors, x and y, vary together. Covariance, the extent to which the values of two factors, x and y, vary together. The closer the data points fall to regression line, the more that the values of two factors vary together. Assumption of test for linear correlation. Linearity, assumption that the best way to describe pattern of data is using a straight line. Pearson correlation coefficient assumes linear relationship, as do most standard statistic techniques. However, the social world is not always a linear place. Be critical about the methods you use, explore and know your data, know your theory. Homoscedasticity. Equal variances at data point disappeared along the regression line. Equal variance of y for different values of x. Graphically, points more or less equally scattered around. Violation of homoscedasticity, heteroscedasticity. A higher value of x results in more variance of y. Normality. Pearson's correlation coefficient R assumes normality. Data points are normally distributed. Normal distribution of x, y, and for normal distribution of y for each value of x, and vice versa. So 3 things for assumption test of linear correlations: linearity, homoscedasticity, normality. Limitations in interpretation: causality, outliers, and restriction of range. Causality: a significant correlation shows the different direction and the strength of a relationship between two factors. Reverse causality occurs that the direction of causality for two factors cannot be determined. Hence, changes a factor A could cause changes in factor B, or vice versa. Problem that arises when the direction of causality between two factors can be either directional, confound variable, third variable has an effect of both original variables, is an anticipated variable not accounted for in a research study that could be causing or associated with observed changes in one or more measured variables. Coffee examples. Lecture: drinking coffee may prevent depression, scientists say. Direction of causality is unclear because the two variables were measured at the same time. 3 preconditions for making a causal claim: empirical evidence, temporal sequence, causality claims supported by reason and theory. Outliers. Outlier scores that fall substantially above or below most other scores in a dataset can change the strength and direction of a correlation coefficient. Restrictions of range. A problem that arises when the range of data for one or both correlated factors in a sample is limited or restricted compared to the range of data in the population from which the sample was selected. To avoid a problem of restriction range, the direction and strength of a significant correlation should only be generalized to a population within the limit range of measurement observed in the sample. Bivariate statistics. Independent variable that we expect to influence another variable in the model. Dependent variable that we expect to be influenced by the least independent variable in the model. Linear regression and multiple regressions. From relationship to predictions, remembering the correlation coefficient R can be used to measure the extent of which two factors, x and y, were related. The value of R indicates the direction and strength of correlation. Whenever R is negative, two factors change in opposite direction. When R is positive, two factors change in the same direction. The closer R is to minus plus 1, the stronger the correlation and the more closely two factors are related. Linear regression, statistical procedure used to determine the equation of a regression line to a set of data points and to determine the extent to which the regression equation can be used to predict values of one factor, given known values of a second factor in a population. Predictor variable or known variable x, the variable with values that are known and can be used to predict values of another. Criterion variable or to be predicted variable y, the variable with unknown values. Linear regression is used to predict values y. Assumption of regression analysis. Linearity. The type of regression analysis we have discussed assumed linear relationship between the FORFs and the DVs, just like Pearson's. In case of non-linear relationship, this model will not fit the data well. Lack of multicollinearity. There should be no strong correlation between any two IVs. General rule, no two IVs should correlate. Diagnostics available in SPSS that test for multicollinearity. Multicollinearity is problematic because it can lead to incorrectly high p-values in t-test, and underestimation of R2 and variable coefficients, typically fixed by removing from the model one or more variables causing multicollinearity. Homoscedasticity. This is assumptions of regression analysis. With homoscedasticity, we assume a variance of a residuals to be constant for all values of the EVs. In other words, the accuracy of our prediction should not depend on the value of one or more IVs, similar to Pearson's. What makes the regression line the best fitting line? its simple regression, we try to predict y with x. We do this by trying to express y as a linear transformation of x. The regression line represents the predicted values of y. These predicted values do not always correspond to actual values of y. Prediction error. Distance between actual value and predicted one, the criterion used to determine the equation of regression line in the sum of squares, of the sum of the squared distances of data point from a straight line. The line associated with the smallest total value of SS is the best fitting straight line, regression line. The method of the least squares is used to square the distance that each data point falls from the regression line and sum of the squares distances in order to determine the line associated with the least squares or the smallest possible value SS. SS is calculated by squaring all prediction errors. The slope and y-intercept of a straight line. Equation of a straight line slope means how I change as x increases, and y-intercepts is the value of y. B, or the slope of straight line, a measure of how much a regression line rises or declines along the y-axis. We do this to try to express y as a linear transformation of x. Introduction to multiple regression. Often the changes in a single prediction variable do not allow us to accurately predict changes in a criterion variable, so our predictions to many behaviors improve when we consider more information. Multiple regression, statistical procedure that includes two or more prediction variables in the equation of a regression line to predict changes in a criterion variable. To accommodate more predictor variables in the equation of a regression line, we add the slope b and the predictable variable x. Advantage of including multiple predictors of a regression equation is that we can detect the extent to which two or more prediction variables interact. Introduction to regression analysis. Regression analysis is the most common used multivariate technique to test causal model in behavior sciences, for experimental researchers, mostly ANOVA. Used in situations where both the independent variables and dependent variable are measured on interval ratio. EV, by the way, is predictor variable and DV is dependent variable. Some central question addressed by regression analysis is how well could we predict the dependent variable using the independent variable? What effect does the independent variable have on dependent variable? And can we generalize our findings to the population? Test of significance. Two main types: simple regression is bivariate and multiple regression multivariate. More than one EV, one DV. A measure for our model goodness of fit at first look of R2. Once we define a regression line, we will want to know how well our model actually fits the data. For this, we look at a measure of goodness of fit. R2 tells us what proportion of the variance of the DV can be explained by the IV. R2 ranges between 0 and 1, regardless of what direction the slope is. Graphically, the closer the dots are in the line, the higher is R2. On standardized and unstandardized coefficients. While the unstandardized coefficients can take on any value, the standard coefficient is standardized to take one value between -1 and 1. The standard coefficient is used to make statements on the strength and direction of effects of an independent variable. It is interpreted similar to Pearson's. In a simple regression, the standard coefficient is the Pearson's R. Making inferential statements with regression analysis. To make inferential statements, two types of tests of significance are calculated as part of regression analysis. An F-test to test the significance for the model as a whole. H1 is the population, R2 is 0. One t-test for each individual independent variable. H0 in the population, the effect of the given independent variable is 0. From simple to multiple regression analysis. As we already seen in multiple regression, we have more than one independent variable. We will also have more than one standardized coefficient, understanding coefficient, and t-test. If all independent variables would be 0, we expect y constant. Interpretation of under standardized coefficient. With h increase by 1 unit, we expect happiness to decrease by 0.0 something something. Interaction effects. When we have more than one independent variable, we might encounter interaction effects. In multiple regression, thus distinguish between main effects, interaction effects, the type strength of the difference of one independent variable has on the dependent variable. Chapter 17. Non-parametric test. Chi-square. Parametric tests, hypothesis tests that are used to test hypotheses about parameters in a population in which the data are normally distributed and measured in an interval or ratio. Non-parametric tests, hypothesis tests that are used to test hypotheses that do not make inferences about parameters in a population, to test hypotheses about data that can have any type of distribution, and to analyze data on a nominal or ordinal scale of measurement. Examples: research in which we count the numbers of participants or items in 2 or more categories. The variances can only meaningfully convey differences when the data are measured on a scale in which the differences that people deviate from their mean is meaningful. That does not happen in nominal or ordinal scales. Non-parametric tests do not require that the data in the population be normally distributed. Chi-square test, statistical procedure used to test hypotheses about the dispersancy between the observed and expected frequencies for the level of a single categorical variable of 2 categorical variables observed together. Chi-square goodness of fit test, used to determine whenever observed frequencies at each level of one categorical variable are similar to or expected to each level of a categorical variable, used to test the H0 that an ordinal nominal variable has a certain distribution in the population. The frequency observed, FO, is the count of frequencies of participants recorded in each category or at each level of categorical variable, and the frequency expected, FE, is the count of frequencies of participants in each category or at each level of a categorical variable as determined by the proportion expected in each category. Multiply the total number of participants by the proportion expected in each category. Chi-square test, again, is statistical procedure used to test hypotheses about the discrepancy between the observed and expected frequencies. H0 in the population, something happened. H1 in the population, it's not true that something happened. The test statistic measured the size of the discrepancy between an observed and expected frequency at each level of categorical variable. The larger the difference between emergently observed frequencies FO and the expected frequencies FE, the smaller the probability the H0 is true. The degrees of freedom for each chi-square distribution are equal to the number of levels of each categorical level k minus 1, df k minus 1. The critical values of a chi-square test increases as the number of levels of the categorical variable k increases. As the df increases, the critical value also increases. Chi-square distribution. Positively skewed distribution of chi-square values of all possible samples when H0 is true. The rejection region is always placed in the upper tail of positively skewed chi-square distribution. Hypothesis testing for goodness of fit. We compare the value of a test statistic within the critical value of a test. Statistic falls beyond the critical value when we reject the null hypothesis. Conclusions. A chi-square goodness of fit test showed that the frequency was similar to what we expected, state numerical result of chi-square and p. Interpreting the chi-square goodness of fit test. Interpreting a significant chi-square goodness of fit test compared observed and expected frequencies at each level of a categorical variable, because this is how the test statistic measured the discrepancies. It cannot be interpreted in terms of differences between categories. Using the chi-square goodness of fit test to support the null hypothesis, a decision to retain the H0 is the goal of the hypothesis test. There is no reason to think H0 will not be true based on previous research. Independent observations and expected frequency size. The observed frequencies are recorded independently, meaning that each observed frequencies must come from different and unrelated participants. The chi-square test for independence. The chi-square test of independence used to determine whenever frequencies observed as a combination of level of 2 categorical variables are similar to frequencies expected. Used to test the H0 that 2 ordinal nominal variables are not related to each other in the population. H0, there is no relationship between the 2 variables in the population. H1, there is a relationship between the 2 variables in population. To find the expected frequencies in the row and column total are equal, we divide the number of participants observed by the number of cells to find the expected frequency in each cell. To find the expected frequencies if the row and column total are not equal. The statistic is the same as the one for a chi-square goodness of fit test. Hypothesis test for independence. We compare the value of the test statistic to the critical value. If the test statistic falls beyond the critical value, then we reject the null hypothesis. Conclusion. Example of rejecting H0. A chi-square test for independence showed a significant relationship between the data indicate is associated with. Chi-square. Step is significance testing. Formulate H0 and H1. For both chi-square test and H1 is always non-directional. H0, no relationship between two categories. H1, there is a relationship. Calculate test statistic. In order to calculate chi-square, we need to construct a FE table and apply the result to formula. Find appropriate critical value given alpha and df. For the chi-square test for independence, the df is number of rows minus 1 or number of columns, x number of columns minus 1. For the chi-square goodness of fit test, the df is k minus 1. Compare obtained and critical value and decide whenever to reject H0, obtained, critical, reject. So test of independence, number of rows minus 1 plus number of columns minus 1. Type of statistics, descriptive and interferal, uni and bimodulate. Types of variables, continuous and discrete, level of measurement, interval, ratio, ordinal and nominal. Key concept, inferential statistics. Population, the group about which we want to generalize. Sample, a set of cases. Sample design, the procedure used to select the cases for the sample. Sampling bias is a bias in the sample because by the flawed sampling procedure. Sampling error, a deviation of a sample characteristics. We always have to assume a certain degree of sample error. Inferential statistics give us a tool to deal with uncertainty. Test of statistical significance. Statistical techniques that help us to decide to what extent findings from a sample can be generalized to the population. In inferential statistics, we typically assume our interval ratio variables to be normally distributed, meaning unimodal, symmetric, asymptotic to x-axis, and then theoretical. More bivariate statistics. Cross table, cross types, contingency table, independent variable, variable that we expect to influence another variable, dependent, the one that's being influenced. Cross tables, table that depicts a possible relationship between an independent and dependent variable. What does this table tell us about the relationship between the two variables? Percentages. When calculating the percentages of the column total, we always compare percentages horizontally. To determine the relationship in a crosstab, put the independent variable in the column and dependent variable in rows. Calculate percentages of column for easy interpretation. Compare percentages horizontally within a categorical or dependent variable. Steps in significance testing. Formulate H0 and H1. Determine level of significance. Calculate the test statistic. One sample z-test if we know the standard deviation, or one sample t-test if the s-deviation is not known. Find appropriate critical value of test statistic at the level 0.05. Compare obtained statistic with critical value. If obtained statistic is smaller than critical value, retain H0. In this step, reject H0. Confirm that sign of obtained value supports the H1, then directional. State your conclusions referring to the population and as detailed as possible. Mean, context. P-value. When the proportion of the distribution beyond the sample mean is the tail. When P is low, H0 has to go. Remember that to do with P-value in SPSS for directional H1, divide by 2 before comparing to alpha. Z-test is normal distribution, standard error. We know the population standard deviation. The DF is not required. The probability of obtaining a measured sample outcome whenever H0 should be rejected or retained. T-test, T-statistic, p-value, T-distribution, estimated standard error. No, the sample variance is used to estimate the population variance. DF is n-1, the probability of obtaining a measured sample outcome. Homoscedasticity, we assume the variance of the residuals to be constant for all values in independent variables.